Alright, now we're going to do example 1 from 14.7 part 2. So, determine all determine all absolute extrema of f of xy equals 2 plus 2x plus 2y minus x squared minus y squared on a triangular plane bounded by the lines x equals 0, y equals 0, y equals 9 minus x. Alright, so it's helpful, I think, to graph the set D, which is our domain, first, just to get a handle on what's going on. And so I did that here, and it's pretty simple. It's just this triangle here, and it's colored in this light blue. So that's our domain. And if you can imagine Z coming out of the plane here, or out of perpendicular to the xy plane shown here on the screen, then that's where the surface lies. And we don't really know what it looks like. So we're trying to determine the absolute max and mins of that, and it's floating above, or technically it could be through or underneath, that blue triangle. Alright, so first of all, appreciate that it is a closed domain here, and so I'm not going to give you one that's not, but it's, okay, we can go ahead and use all these cool theorems and stuff that we talked about. So don't necessarily have to go in an exact order as these steps, but I'm just going to be consistent with the book here when I do it. The first thing it tells you to do is find values of f at the critical points of f and d. So here we're just going to use the function to find the critical values, and this is what we did in part 1 of this section. So hopefully you remember that that's when the partial with respect to x equals 0 and the partial with respect to y equals 0. So finding those partials, they're pretty simple. And then notice each of them can be solved for a value. And so the and goes between these because they have to be occurring concurrently, I guess is how you can say that. And so x equals 1 and y equals 1 at the same time means at the point 1, 1. So it turns out in this case there's only one critical value, or critical point. So here, I'm again going to follow the steps here. It says to find f there, and so I did that by simply plugging in x equals 1 and y equals 1 into this given function. And so that's like finding the z, or the elevation, or the value of that function, and you get 4. And so this is a candidate for the absolute maximum or minimum of our z function that's in the domain of this blue triangle. Alright, so we have one candidate, is a way to think of it. Now, find the extreme values of f on the boundary of D. Okay, so notice we actually have 3 boundaries defining D. So what this means is we found the critical value that's not on the border, and notice it's good to check here that it is in D. I plotted it right there. It is on our domain, otherwise we wouldn't consider it. So we got that one, but what about the edges? Because it could attain a maximum on one of the edges, or a minimum. And we need to check for that. So we just deal with one at a time. It doesn't really matter which one. And it's going to amount to basically doing 3 separate max-min problems. And then we put all our results together to see collectively what is absolute max or minimum for this problem. So here we go. I got my little picture here, and I just arbitrarily called this boundary here at y equals 0 a, and then the vertical one here b, and the hypotenuse there c. So probably good to start with a or b here, and I just started with a. So notice that's defined mostly by that equation y equals 0, but it also has a stopping place. It has a stopping place at x equals 0 and x equals 9. And so plugging y equals 0 into the overall equation, again, is going to be a good start. And that's what's going on. Now we just have in the vertical or out of the page situation, it only being defined by x, the elevation. That's how you could think of that. And so that's kind of nice because it's boiled down to two variables, and I can just say now what are the extreme values of that. So this is a Calc 1 problem right here, finding the extreme values on the closed interval from 0 to 9. The x's go from 0 to 9 of this function. That's exactly what it is in this case. So this was like the introductory example. I'm going to find my critical values by taking the derivative, and then I get 2 minus 2x and solve for x equals 1. So that's my critical value, but I also have the point x equals 0 and 9 to consider. So at this stage I just put in 0, 1, 9 into the function one at a time to figure out what the values are. And because we set y equals 0 initially for all these, then now we're talking about, hey, this is the elevation. And these are candidates for overall the extreme values of this multivariate function on this domain. So now, in summary, what we have so far is we had a critical value that was on the domain that we found a potential absolute max or min, and now we found a bunch more that is purely on that boundary A. And now we got to check the other boundaries to get all our candidates. So I'm going to go with boundary B because it's kind of the easier situation, and it works out to be really similar to boundary A, both in method and also in formulation because of the way this equation works. So here I'm plugging in x equals 0, and then my function boils down to just something in terms of y on that boundary here. I'm going to take the derivative, set it equals 0, and solve for y. And I get 1. I also need to check the endpoints of 0 and 9, so I put those in here. Just to be clear that you don't actually have to do the one at y equals 0 because technically it's a point right there, a boundary point. And I already did that, and nothing's going to change there, so I just decided to put it in here to show you like, oh yeah, we got the same thing. For x and y equals 0 is what this would say. We get 2, and here's just was kind of done in a different order. Y equals 0, or x equals 0, then y equals 0, and yeah, you get 2. So if you don't want to check that again, it's a little bit of a time saver. But you did not check the point at 0, 9, and so that was necessary, and we got some more candidates. Now we're finally to the border C. So it's a little different than the other two, boundary A and B, because it's y equals 9 minus x. And so what do you do there? Well, kind of a similar thing actually to what we did, is you have your overall function, and for y you're going to plug in 9 minus x, and then it's going to be more complicated, but you're still going to just have an equation that's entirely in terms of x. Another thing to note, sorry to scroll, is that we already have the boundary points here that are defining that hypotenuse there, or boundary C. So I don't have to check those again. All I care about now then is finding critical values on the line. So I can focus on that. Okay, so I described that we can just plug in 9 minus x in for y in this f of xy, and it's kind of complicated. You want to simplify, did that. And we finally get negative 2x squared plus 18x minus 61. Alright, so from here, what do you do? Well, just like we did for boundary A and boundary B, we're trying to find the critical values, just like in Calc 1. So go ahead and take the derivative with respect to x, set it equal to 0, and you obtain x is equal to 9/2. Now plug that into your original equation here, where you let y equal 9 minus x, and that will give you the y that goes with it. You actually obtain 9/2 for that as well. So we're talking about there's something going on, or a candidate, at 9/2, 9/2. So you plug that into the original function and you get a value. So that's like the elevation at x equals 9/2 and y equals 9/2. You get negative 41/2, and we found all our candidates now. So one thing to mention up here in parentheses is an important point here, is that you need to make sure your critical value is on 0 to 9 in the x, because this is where we were. This 9/2, 9/2 is on our triangle, in other words. So now we collect, we're almost done here, we collect all the candidates, and then we just see which one yields the highest or the greatest of the z's, or f of x, y's, which one's the least, and then we just report the greatest as the absolute max and the least as the absolute mins. So here we got a winner for the greatest value of 4. So that's our absolute max, and then negative 61 is tied for the least. So we report those as absolute maxes at 114, absolute mins at 90, comma, negative 61, and 09, negative 61. So that's it for the problem. I did include a graph just so you could this is really abstract to just do all this work, so just trying to convince you that this makes sense. So here we have our endpoints, and we could have had an absolute max or min on any of these boundaries that's forming the triangle, or at the boundary points, which is 3 of them, or on the actual surface that's bounded. And so we checked all those things, and we found that there's a tie for the absolute minimum at these boundary points here shown, and that the absolute maximum happened at the critical point on the surface, so within the region. But we had to check all those places, and you can hopefully appreciate from this that, you know, yeah, you can have an absolute maximum on the boundary point or on the surface boundary, that can occur, and it did occur for the absolute minimums in this problem. Alright, so that's it for this section, and then on to the next one.